Okay, I guess we can start. Sorry, everybody, for the delay. We have a small inconvenience, but finally we are here. Welcome to the season 6 of this Latin American webinars on physics. I'm going to be the host, Roberto, and the speaker of today is a very important physicist. He is John Ellis, that he was kindly wanted to give this webinar. And after a lot of problems with the computer, we make it. And we're going to make a double connection via Hangout and Skype. So it's going to be a little bit messy, but all the information is going to be here. So first of all, we have John. I don't know, John, if you can say some few words to the people can hear you only.
Yes, hello. I hope you can all hear me. I'm speaking to you from King's College, London. I should apologize for the technical problems. I don't know what the problem is, whether it's at King's or whether it's with Google. But anyway, I'm really glad now to be with you.
Yeah, very good. So for all the people that is following us in YouTube, John Ellis is a world-class physicist. He he did his PhD in Cambridge University, and after some postdoc in SLAC and Fermilab, sorry. Anyway, he spent most of his career at CERN, around almost 4 decades, and now he is at King's College of London. So, John, it's a pleasure. It's very nice to have you here, and you can start your presentation when you want. Let me just share my screen. And oops, where is John? I lost your screen, John. Sorry, 1 second. Okay, if you can share your screen now, you can present. Yeah,
I'm sharing my screen. Do you not see it?
No, I don't see it. If you can share it again, just stop and restart the screen share. We can.
Okay.
We are having some dots from Skype, John. So it seems that it seems for the moment that the screen is not, we are still having some technical problems. We are gonna solve the problem now. 1 second. So I don't know if you can. Okay, we're still waiting for the connection. It seems that also he's having problem since that the reason of the problem is something related with the firewalls in King's College. So for the moment, we are still trying to connect. If it is not possible, yeah, there is some, I don't know if you can see the connection from my side. Yeah, because I'm not sharing the screen with you guys, but you can see that we're still waiting for his connection, his video. Let me just try to call him again, if Skype allows me to do it. Okay, it seems that it's what will happen in the live streaming. So if you give me just some seconds, we're gonna fix it again, as it's all the time it happens. One second, just to have a small conversation with John, and we're gonna be live again soon. Okay, we're gonna be soon again. Sorry. 1 second. For the moment, I leave you with the screen.
Roberto, puedes mirar el chat.
Okay, everybody, we're back. We fixed the problem. This is the nice stuff of the live transmission, live streaming. So if John now, if Skype allow us, at the end is a conversation between Google and Apple and Microsoft, sorry. So if everybody can see this, we can start.
Yes.
So John, the stage is yours.
So Roberto, how long should I talk?
As much as you want, but less than 45 minutes, 40 minutes. It's okay.
Yeah, okay. So again, thank you very much for the invitation to give this talk, and I apologize for the technical problems. So let me start off straight away with this inspirational picture, which was taken somewhere in Latin America. So you guys should be able to tell me where it was taken. Anyway, particle physics today, I think, is largely dominated by the recent discovery of the Higgs boson. And here you see Peter Higgs. It's a picture taken in 1965 when he was working out some details of his theory. So I think with this audience, I don't need to remind you about the structure of the Standard Model. Here in the bottom part of the slide, you see the Standard Model Lagrangian. So the first line describes gauge interactions, the second one, how those interactions work on the fundamental fermions, and the two bottom lines, that describes the Higgs sector of the theory. So the third line, the Yukawa interactions that give masses to fermions, and the bottom line, the Higgs potential, and the mechanism for actually giving masses to the gauge bosons. And I think it's worth remembering that there were no direct tests of those two bottom lines before 2012. And one of the things that I'll be discussing is how far along we are in terms of testing that and where we can go in the future. So the next slide shows you what's often called the Stairway to Heaven. And this is a summary from Atlas of the many, many measurements that they have made of standard model processes involving QCD, electron weak gauge bosons, jets, and of course, the Higgs boson. And of course, although we theorists can be very proud, I am sure that we would have preferred it that they find some significant discrepancy from the standard model, but none has showed up so far. Okay, so let's focus in now on the Higgs boson. And here in the top half of the slide, I show you the couplings of the Higgs to vector bosons on the left and to fundamental fermions on the right. So coupling to bosons were actually discussed in quite some detail by Peter Higgs in the paper he wrote in 1966. And I recommend that to anybody with a historical interest. As far as I know, the couplings to fermions were first noted explicitly by Steven Weinberg in 1967. So my own interest in the Higgs boson started in 1975 when, together with Mary Gaillard and Dimitri Nanopoulos, we made the first, I think, attempt at a systematic survey of what the properties of the Higgs boson might be. Now, of course, back in those days, the Higgs was regarded as something very speculative. You know, the senior gray-haired physicists regarded it with suspicion. And for that reason, we were a little bit tentative when we said that we do not want to encourage big experimental searches for the Higgs boson. We did want people to know what it might look like in their experiments. So that was 1975. The next slide comes from 1984. This is the first physics of LHC workshop held in Lausanne. And I got the job together with Graciela Gelmini from Argentina and Henrik Kowalski of reviewing the possible new physics that you could do with the LHC. And of course, we put a lot of emphasis on the Higgs boson, shown in these two diagrams, but also on supersymmetry, which I will return to later on. So continuing with the Higgs boson, this slide shows you the dominant production mechanisms for the Higgs boson at the LHC. So the top line, the dominant production mechanism is gluon-gluon fusion to make a Higgs through top loops. Then you've got, for example, in red, vector boson fusion, massive vector boson fusion. In green, you've got associated production with the W or Z. And then in purple, you've got processes for production in association with the top quark, either TT bar pair or a single top quark. So we should consider ourselves very lucky that for a Higgs boson weighing 125 GeV, many of these mechanisms are accessible to experiment. And in fact, most of them have now been observed. In fact, just yesterday, there was a seminar at CERN by Atlas where they reported 4 sigma evidence for TT bar Higgs associated production. Okay, so I expect that most of you are familiar with the Large Hadron Collider at CERN, so I won't dwell on it. Let me go directly to the measurements that have been made at the LHC so far. So in this picture here, you see the measurements of the Higgs mass from a combined analysis by Atlas and CMS. And you see that already with those run-one measurements, they got an accuracy of about 2 per mil on the mass of the Higgs. Now, I might mention that subsequently, both Atlas and CMS have come up with measurements based on run-2 data. And I highlight here the measurement by CMS of the Higgs decay into ZZ star into 4 leptons, which already has a smaller error than the overall uncertainty in run-1. Now, of course, measuring the Higgs mass is important because it enables us to make precision tests also of Higgs couplings. But I'd like to spend a bit of time discussing another important aspect of the Higgs mass measurement, which is its importance for the stability of the electroweak vacuum. So on this slide here, I discuss the renormalization of the Higgs self-coupling in the standard model. So the Higgs self-coupling lambda renormalizes itself. Now that renormalization has the effect of increasing the self-coupling lambda as you go to higher renormalization scales. On the other hand, in the standard model, with the measured values of m Higgs and m top, the dominant renormalization is actually due to the top quark, and that renormalization is negative. It's very sensitive to the mass of the top quark, as we discuss in just a moment. In the standard model, that renormalization drives the quartic coupling negative at some scale, capital lambda, which you can see here is estimated to be somewhere around 10 to the 9, 10 to the 10 GeV. And I show here a calculation by de Grassi et al. Now, when the Higgs self-coupling goes negative, it means that the brim of the Mexican hat turns down at large field values, and there is a lower energy state, and our present vacuum is unstable. Now, that's within the standard model. My take on this is that we should look for physics that stabilizes the vacuum, and one possibility is supersymmetry, although there are other possibilities for new physics beyond the standard model that could stabilize the vacuum. So this picture here illustrates the problem. So on the left, we have the profile of the Mexican hat, and the top quark turns down the brim of the Mexican hat, and you get this instability indicated by the red arrow, and the red dot goes into a region where you've got negative vacuum energy and where the universe stops its expansion and instead collapses into a big crunch. So here is a formula by Butazzo et al. That describes this instability scale parametrically in terms of the Higgs mass, the top mass, and the strong coupling constant. And if you put in the current determinations of those, you get an instability scale, as I said, around 10 to the 9, 10 to the 10 GeV. So in the top right, the green ellipse indicates the world average values of m Higgs and m top. So m Higgs is by now well established. M top is still more uncertain, and as you can see, that's the principal uncertainty as to whether we're really in the unstable region or the stable region. And since that world average was made, there have been additional determinations by the various Hadron Collider experiments, although all of them, as you see, are outside the stability region. And here, just for good measure, I show another calculation by Bednikov et al., which also indicates that the Higgs mass and the top mass are in this unstable region. Okay, so we've got a precise Higgs mass. It's a puzzle for cosmology. What about its decays? So the Higgs decays should be proportional to their masses. And this picture here shows you the pattern of Higgs decays that you might expect as a function of the Higgs mass. Notice that the dominant production mechanism of the Higgs through gluons is a loop process, and also the prominent Higgs into gamma-gamma decay is a loop process. So it's kind of ironic that the most prominent mechanisms, the couplings of the Higgs, are quantum loop diagrams. Again, we're very lucky. With a Higgs mass of 125 GeV, there are many possible reduction and decay modes of the Higgs. Whereas, if just saying the mass had been 750 GeV, then we would have had a lot more problems. So this is what we expect for the decays of the Higgs. So I mentioned that the Higgs into gamma-gamma decay is very distinctive, but it's also very rare, 0.2%. And the decay into ZZ star into 4 leptons is also rather rare. But the dominant Higgs decay mode should be Higgs into BB bar. that this is still not being discovered at the 5 sigma level. So what do we know? So this plot shows you a compilation of ATLAS and CMS data from run 1, organized from top to bottom according to the Higgs production mechanism and the Higgs decay mode, so gamma gamma, ZZ, WW, and tau tau. So there have been lots of measurements, but as I said, still Higgs into BB bar has not been discovered at the 5 sigma level. Higgs into mu mu is something we'd like to see, a second generation mechanism. TT bar production, that's maybe now emerging, although still only at the 4 sigma level. And for the future, we would like to see Higgs production in association with a single top. So 3 years ago, with my then student, Tivong Yu, we said, look, if Higgs couplings should scale proportional to mass, what are the data telling you? So we did a fit where the couplings were taken to be proportional to mass to the power 1 plus epsilon, and we fitted epsilon. And as you can see here, the value of epsilon is very close to 0. So the red line is the standard model prediction, the dashed line is the best fit. Everything is consistent with this particle being a Higgs boson, and for that reason, in our paper, we wrote that this particle walks and quacks like a Higgs. Now, subsequent to our analysis, a much more precise analysis has been done by the ATLAS and CMS collaborations, but again, you see the same thing. The data are completely consistent with the standard model expectation. So, do we have any reason to expect that there is physics beyond the standard model to be discovered tomorrow? And I would base my answer on this movie poster from James Bond with a couple of small modifications. And I paraphrase the title of the movie: "The standard model is not enough." And in honor of James Bond, I give you 007 reasons for thinking there must be physics beyond the standard model. So 001 is this instability of empty space that I just discussed. 002 is dark matter, which I'll return to later on. 003 is the origin of matter itself in the universe. I won't say so very much about that in this talk. There's also a problem of neutrinos and their masses. There's a problem of the hierarchy of mass scales in physics. Why is the universe so big and old? We think that's because of cosmological inflation, which again I would say cannot be explained within the standard model. And of course, we want a quantum theory of gravity. So I could go on, but I think that these 007 reasons already indicate there has to be physics beyond the standard model. And many of these issues are being addressed by LHC Run 2. For example, a better measurement of the top quark may give us more insight into the stability of the vacuum. LHC experiments will look for dark matter. They will look for particles that may mitigate the hierarchy problem, and so on. Now, I make no secret of the fact that my favorite extension of the standard model is supersymmetry, and I will spend some time later on discussing what are the remaining prospects for discovering supersymmetry. So let me first of all discuss this issue of the hierarchy of mass scales in physics. So this is a slide that I stole from Nathaniel Craig, where he discusses many different attitudes towards the hierarchy problem. Some people say there's no problem. Some people say, well, we just have to tune the parameters motivated by anthropic reasoning. I don't like those approaches, and I prefer to think that there is some new physics, and I'll discuss a couple of those in a moment. Now, I should say that there are many ideas for new physics, and I compare them to this World War I cartoon, where there are these beyond the standard model theorists being bombarded by data that did not show evidence for their theory. And one of them is saying to the other, if you know of a better whole, go to it. And that's exactly what I feel about supersymmetry. Okay, supersymmetry is being attacked by experiment, but I still think it's better than the other holy theories. Okay, so let's talk a little bit about the hierarchy problem. So as you know, there's two different attitudes towards the Higgs. Either it's elementary or maybe it's composite. If it's elementary, then when you calculate loop diagrams, you get quadratic divergences, and the favorite approach is to cut them off at a scale of the order 1 TeV with supersymmetry. So that's the left hypothesis. And then there's what I call the alt-right hypothesis, which is that instead the Higgs is made up out of fermion and antifermion pairs, just like the Power and QCD. Maybe those are bound together by some. Many of the older ideas about that are not so successful, but one idea which is very popular at the moment is that the Higgs is a pseudo-Nambu-Goldstone boson of some new broken strong interactions. So a convenient way for discussing this hypothesis is a phenomenological framework where you write down the same interactions that you would have of the Higgs in the standard model, but you allow basically arbitrary coefficients, which I've highlighted here in red. So the Higgs vector boson couplings A and B, the Higgs fermion couplings C, and so on. And these couplings will be equal to 1 in the standard model, but maybe they're not 1, maybe they differ. So experimentalists have analyzed this, and for some reason best known to themselves, they make things more complicated by not talking about A, B, and C, but by talking about parameters kappa. So this is a plot taken from a paper by the W50 collaboration. So in orange, we have the Higgs measurements, which tell you that the Higgs coupling to vectors and to fermions is sort of compatible with unity. What's interesting is to combine those data with the precision electroweak data, shown here in blue, and then you see you get a much tighter constraint on the couplings of the Higgs to vector bosons and fermions. So this is another analysis which was done by Atlas and CMS, and what I do here is overlay the predictions of some representative composite Higgs models. So these minimal composite Higgs models have a parameter zeta, and as you can see, this parameter has to be close to 0 if you want to be compatible with the data. Anyway, at the moment, you cannot rule out the composite hypothesis, but there's no evidence in favor of it. So an alternative approach is to say, well, maybe the Higgs has the same couplings as in the standard model on slide 2 of my talk, but in addition, there are higher dimensional couplings, for example, couplings of dimension 6. So if you write down all the dimension 6 couplings compatible with the symmetries of the standard model, you get thousands of them, literally thousands of them. On the other hand, if you are interested in testing just a subset of the data, precision electroweak, Higgs data, and triple gauge couplings, you can simplify matters, you can ignore all the complications of flavor and focus on a relatively limited set of couplings. So that's what we did in this plot that I show you here on the right. So I'm afraid I don't have time to go through the definitions of these dimension 6 operators. Anyway, this particular set of 6 operators is constrained by Higgs production, shown in blue, by LHC triple gauge couplings, shown in red. Black is the global combination, and the black is if you allow all the operators to be switched on simultaneously. If you just switch them on one at a time, you get the green error bars, which of course are much more precise. Now, I'd like to emphasize again that the Higgs couplings should not be considered in isolation. There are also important constraints coming from triple gauge couplings, which are illustrated here. So this paper by Falkowski et al. Illustrated that the triple gauge couplings, shown in orange, and the Higgs couplings, shown in green, are largely complementary, and you put them together and you get the blue constraints, which are much more precise. Okay, so here's another slide which I stole from Nathaniel Craig, and I really emphasize the fact that I'm a fan of supersymmetry. But one of the problems is that there are many different supersymmetric scenarios: compressed spectra, R parity violation, minimal models, not so minimal models, natural models, unnatural models, etc. So one of the complications, as I like to say, is that there are no signposts in superspace, and we have to look at many different models. Now, perhaps I should have already emphasized that I like supersymmetry, as you know, and here I've written it in the largest font that will fit on the slide. I would argue that LHC Run 1 has actually given us 3 additional reasons for loving SUSY. One is that it stabilizes the electroweak vacuum, the issue that I discussed at the beginning of the talk. SUSY also makes a successful prediction for the Higgs mass. It should be less than 130 GeV. It also predicted correctly that the couplings should be within a few percent of the standard model values, as we saw earlier in the talk. And of course, these reasons for loving supersymmetry should be added to all the previous ones, like the naturalness of a hierarchy that I mentioned, grand unification, string theory, and dark matter, which I will return to in a moment. So this slide I can probably skip over. I'm going to be working within the minimal supersymmetric extension of the standard model, so the MSSM. So of course, the experiments have been looking very hard for evidence of supersymmetry, and no supersymmetry yet. They've also been looking for other more exotic physics, and they haven't found anything of that either. They haven't found black holes, they haven't found any of these other hypothesized new physics. So I think that everyone is a bit puzzled at the moment how to continue the search for new physics at the LHC. Should we just continue with the same models as previously? Should we be thinking about new models? Should we be thinking about unexplored corners of, for example, supersymmetric parameter space? Should we be thinking about novel signatures that perhaps have not been studied fully? So I am engaged in an effort together with a group of theorists and experimentalists called Mastercode to analyze the constraints on different supersymmetric models, incorporating all the available data. So we incorporate the data coming from precision electroweak observables, actually many more observables than are shown here. We also incorporate many flavor observables coming from B decay, also from K decay. We incorporate the constraints from dark matter. So there is the overall density of dark matter. And there is also constraints on the spin-independent and spin-dependent scattering of dark matter on regular matter. And of course, the LHC observables. So in all this, are there any hints to new physics? Well, of course, there's been this long-standing puzzle about the anomalous magnetic moment of the muon. And as you can see here, the current discrepancy between the Brookhaven measurement and the best theoretical estimate in the standard model is about 3.5 standard deviations. Maybe not conclusive, but the good news is that soon Fermilab will do a repeat experiment. Another area where there seem to be significant anomalies is B into strange quark plus dileptons. And I'll say a little bit about that later on, but not very much. I think it's very difficult to explain in at least the sort of supersymmetric scenarios that I've been studying. So here I show you a typical spectrum from a global fit that we are about to release in the phenomenological MSN, or PMSSM. And so what you see here is the MSSM spectrum. And the point I would like to emphasize is that in this model, at the best fit point, a lot of supersymmetric particles are accessible to future runs of the LHC. So you see here that many of the squarks are accessible to the LHC. Leptons may be more difficult. Maybe one could also look for some of the electroweak ENOs. Now, what we also find in this model is that there are a couple of other possible LHC signatures which are worth exploring. So these spiky lines that you see here are for various fits to LHC 13 data, the dashed lines into LHC 8, fits with G-2, the solid lines, and sorry, the blue lines, and without G-2, the green lines. Now, an interesting thing here is that, well, if you believe in G-2, it turns out that the next to lightest supersymmetric particle probably has a short lifetime, less than 10 to the minus 10 seconds. But if you're not sure about G-2, and you look at the green lines, you see that the next to lightest supersymmetric particle lifetime could be as long as 10 to the plus 3 seconds at the 95% confidence level. Actually be cut off at 10 to the plus 3 seconds because a longer lifetime would give you problems with Big Bang nuclear synthesis. So a long-lived sparticle is a potential signature in this model. Another interesting thing to look at is Bs goes to mu plus mu minus decay. Now, this plot is maybe not tremendously clear. Now, what you can see is that there is a preference for a value of this decay close to the standard model. But the decay could be significantly smaller. And in some of these fits, the best fit value is something like 0.8 of the branching ratio in the standard model. And I remind you that the best fit to the current experimental data is actually below the standard model value. So this is maybe something worth watching. Now, as I said, there's been a lot of excitement recently about possible anomalies in B goes to K and K star mu plus mu minus decays. And these are a couple of plots taken from one analysis in terms of the coefficients of operators 09 and 010 with muons and with electrons. So the data indicate that there might be a contribution beyond the standard model, C9 for muons. C9, as you see, has a vector-like coupling to muons. Other couplings cannot be excluded, but that's the thing that seems to be most indicated. Now, I personally prefer to take a sort of wait and see point of view. I think it's very difficult to explain this with supersymmetry, but there are many phenomenological models involving additional Z primes and leptoquarks, which might be able to explain this. So now let me turn to the search for dark matter. So, as you know, there have been many experiments looking for spin-independent dark matter scattering, and the existing limits are shown here with solid lines, and prospective future limits are shown by dashed and dotted lines. Actually, this is a bit out of date, because as you'll see in a moment, there have been some more upper limits on spin-independent dark matter scattering since this compilation was made. So here, I note also in yellow at the bottom, the neutrino floor. This is the background coming from astrophysical neutrinos. And in pink here, you have what at least Laura Bodis considered to be the possible range of predictions in supersymmetric models. So here I show our predictions in this phenomenological MSSM that I mentioned a moment ago. So here you see some of the more recent limits from Lux, Xenon, 1 ton, and Panda X. As you see, according to our analysis, the dark matter scattering rate in the phenomenological MSSM could be close to the current limit, but it might also be below the neutrino floor. Now, in addition to searching for spin-independent dark matter scattering, there are also experiments looking for spin-dependent dark matter scattering. The current best limit, direct limit, comes from the Pico experiment. And here we compare the predictions of our phenomenological MSSM study with the Pico limit, and you see that, again, it could be quite close. Okay, so I've talked about dark matter experiments. I've talked about past LHC results. Here is the perspectives for future runs of the LHC. So now we're coming towards the end of 2017. The LHC has been running extremely well. It's accumulated something like 40 inverse femtobarns this year to add to the 35 or so that it had previously. It will run again next year, and then there will be a shutdown. Following that shutdown, it's hoped to push the integrated luminosity up to about 300 inverse femtobarns, so about 10 times more than have been analyzed so far. And then there will be a further upgrade to the high luminosity LHC about 10 years from now, which eventually should take the integrated luminosity to about 3,000 inverse femtobarns, so almost a factor of 100 more than what had been analyzed so far. So this is to say that there's still good prospects for discovering new physics in that 100 times more data. However, obviously, people are thinking about what might be a possible future collider beyond the LHC. And one of the ideas that's being discussed both at CERN and in China is the idea of a future circular collider. So here the idea is to go to something like 100 TeV in the center of mass in proton-proton collisions, and to have very high luminosity E+ E- collisions, of course, at low energies. And that gives you a combination of exploring the 10 TeV scale directly in proton-proton and indirectly through precision measurements in E+ E-. So that's the vision which is shared by both CERN and China. The picture here shows you how such a large 100-kilometer circumference collider might be located near CERN and going around Geneva. Now, when one talks of E plus E minus colliders, of course, there's different options on the table, which are illustrated in this slide here. So in red, we have the large circular collider option that I just discussed. And I highlight in this ellipse the fact that it can give you extremely high luminosity at low energies, which will enable you to have unparalleled accurate measurements of the Higgs and also electroweak measurements. Another possibility for the future is to build a linear E plus E minus collider, and the highest energy proposal is the one outlined here in green, CLIC, which would run parallel to the shore of Lake Geneva, close to CERN. Now, these can be compared with the ILC, highlighted here in blue. So the ILC doesn't go to such high energies, doesn't have such high luminosities, but maybe it's a proposal that is more ready for approval. And so we'll see what happens with that. I just wanted to show one plot which illustrates the precision possible with a future circular E plus E minus collider. So I showed you previously this epsilon plot. So here is a possible future epsilon plot. And you can see that the uncertainty in the mass dependence of the Higgs coupling is down at the per mil level. Of course, such a machine would not just do Higgs physics, it would also produce something like 10 to the 12 Zs, 10 to the 8 Ws, millions of tops, and so on. So this 100-kilometer tunnel that I was talking about could house either an E plus E minus machine or a hadron-hadron machine. And of course, a hadron-hadron machine would also produce lots of Higgs bosons. And these are the dominant production mechanisms all the way up to 100 TeV. And here, what's particularly interesting is the possibility of measuring double Higgs production, which will be sensitive for the first time to the, well, perhaps not for the first time, will be the most sensitive way to measure the triple Higgs coupling. And of course, with such a 100 TeV machine, one could also look for heavy new physics, such as heavy quarks and gluinos. And this plot shows you that the reach for quarks and gluinos extends above 10 TeV. Okay, so that brings me to the end of what I was prepared. So the discovery of the Higgs boson has been a great victory for both theory and experiment, but it's also a big challenge for theoretical physics, particularly in the future. Now, is the Higgs boson really as simple as it seems? To many of us, that seems inconceivable, but we don't know which direction to go beyond the standard model. So as I said, maybe the LHC will discover new physics. It's going to accumulate something like 100 times more events than what have been analyzed so far. If the LHC does discover new physics, then surely the priority for the next accelerator will be to study it in detail. Of course, if the LHC does not discover new physics, then we should focus on measurements of the Higgs boson. In either case, in my opinion, a large circular collider may offer the best prospects for particle physics tomorrow or the day after tomorrow. Thank you.
Okay. Thank you very much, John. Let me just go back to the webcam version. Okay, so thank you very much, John. It was super interesting, your talk. And I guess we can start with the session round, but before, just to let the people that is following the streaming or watching this video in YouTube in the future, that you can make comments or questions, write it here in the comment or in the YouTube chat. And so now we can start with some questions for the people that is present here in the Hangout. So if anybody has a question, please unmute yourself and ask it directly to John. So Yeah,
I have a question.
please.
Can you hear me? Okay.
Yeah.
Okay. Thank you very much. It was very nice talk. Regarding this very last point, if the LHC detect nothing, no, new physics, what the main reason to study in deeper the Higgs boson will be to find new physics, or what will be the main reason to focus on the Higgs boson? Why not, or I don't know, focus on look for dark matter or other things?
Okay, so what I was assuming in that line there was that the LHC does not find any new physics, so in particular it doesn't find dark matter. Now, of course, there are non-accelerator experiments looking for dark matter, and those they will certainly continue. But I think if the LHC does not discover dark matter, it's difficult for me to imagine that for example, a low energy E plus E minus collider would discover it. High energy E plus E minus collider, maybe. A large circular collider, perhaps a much bigger chance. But the one thing that one can say is that the Higgs is certainly there, and so this should probably form the core of any program for new physics after the LHC, if the LHC doesn't discover any other new physics.
Okay, thank you.
So is there another question for John? So for the moment, I have some questions. John, when you were talking about circular collider or linear collider, beyond the scope of these searches is to go like, is it possible to do the precision physics with this type of accelerators, with the one that has a lot of luminosity at low energy? Or is more just to try to find new particles by increasing the statistics?
So if you can see my screen,
yes.
You will see that the cross-section, for example, for Higgs production, but I could show you similar cross-sections for other particles. The cross-sections for Higgs production go up by almost 2 orders of magnitude from the LHC to a 100 TeV machine. And the 100 TeV machine, the design would be to get a larger luminosity. So you're going to get at least 2 orders of magnitude more Higgses. So I think then the challenge would be, can one do precision calculations and precision measurements? And probably that's going to be possible. I mean, we're talking, decades away from now, okay? And I think that in between now and then, the experimentalists will learn how to do a more precise job. And I think also we theorists will have time to do a more precise job. So yes, I think with the LHC, with the Future Circular Collider, you could in principle also do precision Higgs physics, although it's going to be tough.
Yeah, but what about the quartic coupling within the Higgs? Because I heard that this type of coupling is kind of a nice starting to see if there is a larger number of Higgses, or if it's the Higgs of the MSSM, or it's a Higgs standard model or something like that.
So that's why I highlight on this slide. You can still see the slide, right?
Yeah.
So that's why I highlight the process of double Higgs production. So the double Higgs production actually gives you sensitive to the trilinear coupling. Now, the trilinear Higgs coupling is precisely predicted in the standard model. And as you say, any deviation from the standard model value would be indicative of new physics, maybe double Higgs, maybe supersymmetry or something like that. So there have been many discussions of how accurately you could measure the triple Higgs coupling with some other accelerator. LHC, I think the prospects are very, very weak. A low energy linear collider, maybe you could get some sensitivity through radiative corrections. CLIC, I think you would have a better chance because you go up to 3 TeV in the center of mass. I don't have the numbers to hand. I think what is clear is that 100 TeV proton-proton collider would give you a more accurate measurement than any other. I might mention that people have also considered measuring the quartic coupling. So here you're sensitive to the triple coupling. You can also consider sensitivity to the quartic coupling. And maybe that's possible, but I think that's going to be very tough.
Yeah, it's much suppressed than the yeah,
right.
Yeah, exactly.
And there's also a problem of the fact that the experimental signature is not very distinctive.
Mm-hmm. Yeah, thank you. Is anybody with more questions? Please unmute yourself and ask.
Yes, just to see if I understood correctly, John, you just say that even in the future circular collider, the prospect for measuring the quartic coupling is super hard?
That's my impression. So
Okay.
there have been a couple of papers on this. Maybe people would like to explore it in more detail. I remember in particular there was a paper by Kazuki Sakurai and somebody a couple of years ago that was one of the first papers on that subject that I saw. So if you're interested in pursuing that, I recommend looking for papers that Kazuki Sakurai has written, papers without me, and see whether there's something interesting there to follow up.
Okay, thanks.
Yeah, I guess Joel has a question. I don't know.
Yes, yeah, thank you. I was trying to ask it. So one of the things that the MSSM doesn't address is neutrino masses, right? So I guess that most people expect that you just embed a high-scale seesaw into the model and just deal with it, right? But I was wondering if you chose another model that could have some impacts on the low-scale phenomenology, what kind of impacts would those be? Would we have?
Right. Well, actually, I think that even if you just glue together the seesaw model and the MSSM, there are potentially interesting flavor-changing signatures, but these would involve sparticle loops. And if the sparticles were relatively light, then obviously those effects would be larger than if they're relatively heavy. So this is not something that I looked at recently with the latest experimental limits on sparticle masses, but I think this is something which is worth keeping in mind. I mean, I'm thinking of processes like mu goes to E gamma, mu goes to 3E, anomalous mu E conversion. And actually, there are experiments, ongoing experiments and proposals to address several of these. I think that's an interesting line to pursue.
Sure. I was actually wondering about collider phenomenology. Sorry, it wasn't clear.
Collider phenomenology. Well, again, this is something that I've thought about in the past. So you might get flavor-changing sparticle decays that you could look for at a collider, but let's first of all find a sparticle. Of course, there are ideas for how you could test various different variants of seesaw models at a collider without invoking supersymmetry. And well, I don't have anything useful to say about them, but they're also worth pursuing.
Okay, thank you.
Okay, anybody has another question for John?
Yes, hello, can you hear me?
Hello.
Yes, hi. Yes, well, regarding the G mu -2, if in the next few years Fermilab confirms like the discrepancy between the standard model and the prediction, and or the measurement and the prediction from the standard model, what would that imply for the collider physics? I mean, would we, if Susie's there, would we guarantee that we find something in the next 20 years at the LHC, or could it still be hiding?
Okay, so I showed you some results from FITS where we take seriously the discrepancy in G -2, and FITS where we discarded the discrepancy. And this paper that we're just preparing will contain a lot more discussion of that. I think it would be very interesting indeed if Fermilab confirms the previous experimental measurement, then I think the onus would really be on us theorists to try to do a better calculation of what's been done so far within the standard model. And there are efforts in that direction. For example, the lattice people seem to be making progress towards a calculation of light by light scattering, and also towards a theoretical as opposed to experimental determination of the hadron vacuum polarization contribution. So that's a scenario that I like, where you have a continuing discrepancy between the experimental measurement and the theoretical calculation, and that would give us lots of things to try to understand. But if the discrepancy goes away, then I think all that tells you is that supersymmetric particles are presumably relatively heavy.
Yeah, I don't know what happened with Federico if he had an answer. But
oh no, thank you. Yes, that's fine. Yes.
Okay, good.
So, John, I have one question before to continue with the round of questions from the people that is in Hangout, that is from YouTube. DC Adam is asking a kind of general question: how would you explore the new physics of extra dimension at CERN? If you have some words about extra dimensions.
Yeah, so people have considered various different experimental signatures. So there's many different types of extra dimensional scenarios. So in some sense, the most conservative scenario actually looks a bit like supersymmetry, but with a more compressed spectrum. And in that case, you would have potentially a dark matter particle, which would be the lightest Kaluza-Klein particle, and that would carry missing energy, but not as much as in supersymmetry. And that scenario maybe should be revisited, because we now know that if there is a missing energy signature in the LHC, it's very small. Well, smaller than in simple supersymmetric models. There's all sorts of other scenarios, right? I mean, there's a famous black hole scenario where gravity becomes strong in extra dimensions and you produce microscopic black holes at the LHC. This is something that people are still looking for, and I think one can expect more stringent results coming from running at 13 TeV. And I think those searches are interesting because they're also sensitive to other scenarios for new physics that produce very complicated events with lots of perhaps relatively soft particles. And one of these that I studied, in fact, together with Kazuki Sakurai, is transitions, baryon number violating transitions mediated by sphalerons. And this is something that was discussed in the 1990s, and then people got discouraged by it. But then in the last 2 or 3 years, Henry Tai has revived the possibility of sphaleron transitions. And in fact, just in the last few days, he's had a new paper out where he argues that there could be sphaleron transitions that would be observable at the LHC. But to come back to extra dimensions, I think there's many different scenarios, and yes, the experiments are still looking for them. I just mentioned a couple.
Mm-hmm. Okay, thank you. I want to continue with another question that was related with the question that was before with Federico. That in one of the plots that you show about with this master code, most of the constraint from dark matter in the case of supersymmetry suggests that the dark matter has to be heavier than 100 GeV. But then it's like a from the spin independent cross section, you have a very like a cliff in the. I mean, you can go to very, very, very low and spin dependent and spin dependent cross section. Yeah, these plots. So the only prediction that can be done with direct detection experiment in the context of supersymmetry is just to say that the dark matter is heavier than 100 GeV. It's not possible to go to lower masses, for instance.
So I think that in the phenomenological MSSM, it's difficult to go much below 100 GeV. You can go a little bit below. Now, I didn't perhaps explain all the colors in this in these plots. I didn't have enough time. I apologize. So the green contour that you see, which goes down to the lowest masses for the dark matter particle, this is actually a 3 sigma contour. And the blue is 2 sigma and the red is 1 sigma. So if you believe in 1 sigma, then the lower limit is significantly above 100 GeV. If you believe in 3 sigma, it could be less than 100 GeV. It just so happens that the 2 sigma contour is about 100 GeV.
So in that sense, other type of dark matter claims, like at lower masses, are impossible for this case, for the phenomenological MSSM. Like if somebody is still believing in Dama signature or something like that, would be impossible in this instance.
So there's a well-known tension or conflict between the results of Dama and other experiments, such as the experiments CREST and CDMS that I show in the left slide. And in fact, there are other experiments as recently, for example, the Chinese experiment CDEX, which has also got an interesting limit in the low mass region.
Yeah.
So I think it's very difficult to reconcile Dharma with conventional dark matter scenarios. I don't know how to do it.
Oh, yeah, that's good. So is there more question from the people here in the Hangout, please?
Yes, one question. Just to be sure, with the current precision, it is possible to affirm now that the instability of the Higgs potential, or we need to wait for more data in the future?
I'm sorry, I didn't understand that question very well. Roberto, did?
Yeah, it was
about the instability of the Higgs potential. It is confirmed now that the Higgs potential is metastable at higher scale with the current precision data.
So you're talking about the behavior of the Higgs potential according to the current data?
Yes. If it is confirmed that it's metastable, or there is still a room to...
Oh. So I wouldn't say that it's confirmed. I don't know whether I can sort of quickly flash back and find the appropriate slide. As I mentioned, the biggest uncertainty is in the mass of the top quark. And there are important hadronic QCD uncertainties in that. And of course, people have tried to estimate those, and that's included in these error bars that I show here. There are people who still question those hadronic uncertainties, and I would hope that with future LHC analysis, it would be possible to reduce those, the experimental side of those QCD uncertainties. There still is a theoretical issue in terms of relating the parameter in the Lagrangian to the pole mass of the top quark, but that I think is understood at the level of probably something like 250 MeV. So that would be a smaller uncertainty than the sizes of these ellipses. But anyway, I think we should not reach any definite conclusion. I don't think we can reach any definite conclusion, at least until we've seen the run-2 data.
Thank you. So any other question? Because here in YouTube, I don't get any other. So maybe it is okay for this webinar, I guess. John, you have talked a lot, and maybe you're a little bit tired with all the stress that we suffer with the technical issues with the transmission. So,
yeah. Well, anyway, thank you for, as I said, the invitation, and thank you for helping with the technical issues. And I apologize for the delay, but I hope, anyway, it was good to meet with you, even if I couldn't actually see you. And so I wish you good luck for the future of the webinars.
Yeah, I mean, we're working on that to make it each time with Ellie with not any problem. But yeah, first of all, I want to thank you for being here and to agree to give this webinar. And this is a special webinar because it was the number 50 of, so we already have webinars from beginning of 2015 when we started. Yeah. And for the people that is now watching the video, just if you like this this idea of the webinars about research topic on physics, you can subscribe to the YouTube channel, and then you're gonna get all the notification when we do, and you can see all the previous webinars that we have done. So for all the people that are viewing us, so we have to celebrate. And if the rest of the coordinators that are here in the Hangout session, sorry, John, that you cannot see us because the webcam is not, you can't see us. But I have here a champagne that I'm gonna just make a small toast for this special occasion. You can see here. I'm just and not make a mess here in the room, my house. Now I'm gonna try to open. This is because it's a special occasion, because it's the 50, and we have done a lot of effort with this webinar. So let's see if I don't destroy my computer. You're gonna see.
So while you're doing that, I'm going to try to get up on the screen another bottle of champagne.
You're sure? Yeah, okay. 3, 2, 1. Oh, it doesn't go. Also technical failure. Oh.
It's not working. Technical problems.
3, 2, 1, honestly. Yoo-hoo! And explode, of course. Okay, so
can you see my screen?
1 second, just John, because I have my hands wet now, just to show to the people that I have my.
I can share it.
Champagne. I can show the screen now. Oh, I can see it. Wait, let me just. Now I have a mess here with the. Oops. Okay, enter screen. Okay. Whoa, we can see your. That is the champagne for.
Okay, so the night before the Higgs discovery was announced, my wife and I had Peter Higgs to dinner, and in our house, and we opened a bottle of champagne. And of course, then the discovery was announced. Everybody was very happy, and then the Science Museum in London asked me to donate our empty bottle of champagne to their collection. So then they sent it on a traveling exhibition around the world, and actually here it is in Singapore. And you could make out a lady in the background. That is actually our daughter, who happened to be in Singapore and who caught the exhibition and took this photo. So anyway, here's the Higgs champagne.
And it has the Higgs potential in the bottom, I guess, no?
Absolutely.
So one question, John, just beside the talk, the photo of the desert, that is, let me guess, it's not the Atacama Desert, no?
No, it's not Atacama.
It's in Colombia or in Peru, maybe?
No, it's actually in Argentina. It's a little bit south of Malagüe, where the Auger experiment is located. So it's on the edge of Patagonia.
Ah. Yeah, because it looked like yeah, for me it was familiar there, kind of. But yeah, most of the desert could look similar then.
Yeah.
Yeah.
But the prints in the soil, those are actually proof prints, and that's a good piece of that's a good clue that it must be in Argentina, because those are gaucho hoof prints.
Yeah, that's nice. Yeah. Oh yeah. Oh, I left a mess here with the champagne. I'm cleaning the. Okay, so again for all the people that is following this the webinar, for you, John, for participating, and I guess we can leave the transmission till here. Just a very small announcement, because with the law physics, next 31st of October we are gonna do a dark matter day. We're gonna participate in this event of dark matter day, and we're gonna use all what we know with the law physics. So we are going to be connected with 3 different institutions in Latin America: Pontificia Universidad Católica de Chile, Pontificia Universidad Católica del Perú, and the Universidad de Antioquia. We are going to be connected and talking about dark matter with different scientists that are working in Latin America. So, John, thank you very much. All the viewers, thank you for watching.
De nada. Con gusto.
And see you next time.
Okay, bye.
Bye.